In this section and in the next one, we are going to study subsets of metric spaces in a quite abstract way. Somehow this is kind of the peak abstraction that we have reached here, and from this section and the next one, so 11.5, this will be the final one for chapter 11, and then we will turn to a bit more concrete stuff and we will turn towards differentiability of functions in general on vector spaces, but focused on functions or maps from Rn to Rm for arbitrary values of n and m. And here we're kind of laying the groundwork. We are doing some abstract stuff that we need in order to formalize some notions that we will need there. And it might be quite abstract and quite hard to follow, but please stay with me. This is kind of basically like set theory on an advanced level. So we're pushing around sets basically and trying to abstractify certain properties of intervals or of subsets of the real numbers that we will need at that point. I hope you get the main ideas. If you don't get every detail of the proof, it's not too bad, but just try to understand the main ideas and the main things that we're doing with this. And in this section, I will focus on so-called open and closed subsets of metric spaces. So before I give you definition, a bit of motivation. When we studied differentiable functions in the previous semester in Mathematics 1, we usually considered functions on open intervals. So we took some open interval I, studied a function from I to R or to C, and then defined the derivative by the differential quotients. Now, just to remind you, the differential quotient, assume we have some function, let's say from I to R, then f prime of x0, assuming it exists, of course. The derivative here in x0 is the limit as h goes to 0, f of x plus x0 plus h minus f of x0 divided by h. So if we take a look at this is first of all we need to define somehow limits of functions which we haven't so far. This will be done in the end of this section. But there's also one important observation, because you cannot define the derivative by knowing the value of f at x0 alone. You need to know the function here for these types of arguments x0 plus h for small h. So we need a little space around x0 where we know the function as well in order to be able to define this limit and thereby define the derivative. Now, the good thing is this is good in open intervals, because if you have an open interval, then for each x0 in I, and this is something you can easily see, there is a little space around this, namely there exists some, let's say again, epsilon bigger than 0, our favorite small number, such that the little space around x0 given by the interval x0 minus epsilon, x0 plus epsilon is completely contained in the interval. So let's say if this is the real numbers here, let's say here's 0, this is the real numbers, and assume we have some open interval, let's say from A to B, and I'm using these parentheses here to indicate this is open. Now if we have any point in the interval, let's say this would be x0, then we can find such epsilon simply so that we stay inside this interval. So let's say we take an epsilon which goes away like this, so this would be the point x0 minus epsilon, and on the other side we would have here x0 plus epsilon, and we might still, the way I've drawn it, take it slightly bigger, but it doesn't matter. Because for this limit to compute, we only need to know this in some of these intervals. So it's sufficient to know the function very close to the point, but not only in the point itself, so we need some space around this point. And this is the notion that we are going to formalize when I talk about open subsets. This is basically a very general version of, generalization of the notion of open intervals in R, but now transferred to general metric spaces. Okay, so this is the main idea behind what I'm doing now. Okay, and with this motivation in mind, let me just give you straight away some definitions related to open subsets of metric spaces, so defining open subsets and some other notions. So first of all, we start very elementary. So 1146 definition, assume we have some arbitrary metric space. Okay, assume we have a point in X, which I also again call x0, and we have some epsilon bigger than 0. We want to formalize this notion that of this open interval here. And in the definitions of continuity and of convergence, we have always used that we kind of need, if we have some fixed point x0, we want to have all x such that the distance from x0 to x is smaller than epsilon. So this would be kind of our the generalization of this. and this we want to formalize as a set. So for this we put B epsilon of x0 simply defined as the set of all x in x, such that the distance from x to x0 is strictly smaller than epsilon. So this is what we will need all the time, basically, this formalism. We call B epsilon of x0 the open epsilon ball around x0. Okay, and the name ball, it's kind of easy to see if you imagine the special cases of R3, for example, but let's first of all consider R2. So let me just scribble some drawings in here. So assume we have R2, and we have some point x0 somewhere in R2, and we have a given epsilon. Then this would mean, if we take the Euclidean distance as we always do, this would mean all points with distance smaller than epsilon for a fixed epsilon. And if we take a look at the geometry here, if we take a look at the Euclidean distance, this just means we get the whole circle of radius epsilon. Whoops. Let's say this is the radius epsilon and assume this is a circle, so almost. So what we have is the interior of the circle there. So maybe let me take another color. So everything that's inside of here, this is B epsilon of x0. Oops, this wasn't too smart. So everything in here except for the boundary curve. The boundary curve would then be the points whose distance is precisely epsilon, which is by definition not contained. So the interior of this here. Now let's consider R3. So add one dimension. So assume we have 3 coordinate axes now. Whoops. So let's say x1, x2, x3. Okay, and assume we have some point in here. So again here, let's say this is x0. Maybe let me drive this. So assume this is our point. And now with the Euclidean metric, if we think about the intuition here, this would be almost the same, but it would be not a disk like this, so nothing flat, but a ball. Everything which is at distance at most epsilon, so this would mean we have a ball around this. So let's draw it like this. Whoops, I hope it's recognizable. So here, and like now the radius of this ball would be epsilon, this point would be x0, but it would be a ball. I'm not drawing the interior now because then you can't see anything anymore. But this is really a 3-dimensional proper round ball in R3. And this is also why we call this the open epsilon ball. And again, the boundary of the ball, so it's only the inside of the ball and the boundary is not contained in there. But of course I have to draw it to make it visible. Okay, this is the open epsilon ball, and this is just, if you have problems with thinking of these abstract notions, think of these images. Think of R2, think of R3, and then kind of try this as the motivational example and always try to think about what does it mean in R2 or R3 if we have the following definitions there. Okay, now part B of the definition, we take a point x0 and x. If we take a subset U of x, we call it a neighborhood of x0. And this is now supposed to be formalize the previous notion. We want to call it a neighborhood if there is a little space around this point inside our set U. So here this would be the open interval, then would be in this term a neighborhood of every point, since we can find this open interval. And in general, we can formalize this with open balls. It's called a neighborhood of epsilon 0, of x0, if there exists some epsilon bigger than 0, such that the little space around x0, b epsilon x0 is completely contained in U. So we have some space around this. This is what we want to express. And if we later on want to define differentiability, this will be kind of the way to go. So to take neighborhoods of a point and then try to find the point, the derivative there. But again, also in the higher dimensional way, to define what the derivative of something in a point is, we need to know the map in the neighborhood, so the values of the map for if we are very close to that point. This is just formalizing this, and so as a drawing, so assume we're in R2. So let's go for some axes here. So assume we have some point x0. So U would be a neighborhood like this. So it's a neighborhood, and this means we can find a circle, so some open two-ball, or in the two dimension we also call it an open disk. Let me draw this in yellow here, which oops, messed up the drawing. So just some round disks. Please think about this as a circle. So this would be B epsilon around x0, and if we take the radius small enough, we are obviously inside of there. Now, a point for which this is not a neighborhood, to give you a counterexample, which also helps to give you some intuition, would be a point here, which sits on the boundary. Of course, it's not contained itself in U, but also if you can take any ball around this point, you would have parts of these open disks which are outside that set. So this would be, this is how we can get something which is not a neighborhood. For example, assume we take a closed interval, so we will see this in form later, a closed interval, so let's say closed and bounded from A to B with A and B included. Then if you take any small interval around A and around B, they will always overlap, so they will not be completely contained in the interval, which makes sense. So this would mean such a closed bounded interval would not be a neighborhood of the boundary points, but it would be a point of each of the points in the open interval between them. This is what we shall discuss in a bit, but this is the idea here. Okay, this is a neighborhood, and now open subsets are simply neighborhoods everywhere. So, yeah, U subset of X is called open in X if for all x0 in U, there exists some epsilon bigger than 0 with B epsilon of x0 subset of U. So in other words, i.e. if U is a neighborhood of each of its points. Of every x0 in U. Okay, this is an open subset. Now, let us see some examples. So this is, I hope you got the idea, but it's good to get things a bit more concrete maybe. And to formalize what I just gave you as examples verbally. So example 1147. Now, first of all, A, B, the open interval from A to B is open in R. For all A and B, so yeah, A could be minus infinity or R, and B could be R or plus infinity. So yeah, why is this the case? If the set is empty, so if B is bigger than R, this might also happen, then we have nothing to show, because every point has such neighborhood because there is no point. There is no such point. So then it's trivially true. So the empty set is open in that setting. But if we have a non-empty open interval, then we have to argue the following. Yeah, for all, note that. First of all, to bring this formalism together with what I just did, for all x in R and R element, R bigger than 0, we get that the open wall of radius R around X. So what is this? The Euclidean distance is just given by the absolute value. So all points which have distance smaller than R from X, this is precisely, just by definition, the interval X minus R, X plus R. Okay, and so this fits in what we did. So this here, what I discussed here was basically just discussing an epsilon ball in R, which is just a fancy way of describing this little interval. Okay, now, if we have an arbitrary point in the interval, so we need to show that we can find some epsilon, or r as I've called it there, some epsilon such that this little interval fits in there. And this we need to prove formally. So if, so for x0 in AB, we put the following, we take a look, so here of course if we take some point, we have to take a look at how much space is there left to A, how much space is there left to B, and then decide for the smaller number and take the correct ball. So we put epsilon to be the minimum, so the smaller space, so the space which is here left from x0 to A, this would be just x0 minus A. And here, from here to there, this segment has length b minus x0. And since x is in the open interval, this is a positive number. So this is the space which is left. So then, by construction, b epsilon around x0, which means x0 minus e, x0 plus e, is a subset of the open interval AB. Hence, AB is a neighborhood of x0. A neighborhood of x0. So, yeah, x0 was, so since x0 was chosen arbitrarily, it follows that the open interval is open. So we've proven that with this notion, with this new definition of openness in metric spaces, open intervals in the old sense are open. So okay, open intervals are open. So this basically means our new notion of openness is just really an extension and generalization of the one we took in the last semester for intervals. So nothing happened actually. So it's really just these notions are compatible with each other. Now, in the same way, we could discuss the closed interval. So this time we take A and B in R with A smaller than B, and we consider the closed and bounded interval AB. Okay, then we can use this same argument because we're staying inside there, so we're actually in the bigger interval. So if we take some point in the open interval here, this will be a neighborhood of every point. So AB is a neighborhood, and now let me abbreviate neighborhood simply with NBHD of every x0 in AB, but not a neighborhood of A or of B. So why is that? For all epsilon bigger than 0, we observe that if we take some epsilon ball around A, and so to show it was a neighborhood, we need to find some epsilon such that we stay in this interval, but this epsilon ball is always A minus epsilon to A plus epsilon, the open interval. And since this is really smaller than A, this can never be a subset of the interval from A to B. This cannot happen. So, yeah, this shows that this is not a neighborhood of A. And the same, of course, for B. There we would have the interval B minus epsilon, B plus epsilon, which would mean that we have numbers which are bigger than B in this interval. And so this can also be not the case. So similar for B. So in particularly, this shows that the closed and bounded interval, while it is a neighborhood of some of its points, but not for all of its points, so this is not open in R. Okay, good news. So this means kind of we have a closed interval which shouldn't be open, otherwise our language would be a bit awkward. So this doesn't happen here. Now, yeah, in the same way, similarly, we can see that if we take semi-infinite intervals of the form A to plus infinity and minus infinity to b with the boundary point included. The open intervals were part of this case 1. So these two are not open in R, simply by just taking this one boundary point that we have and using the same argument we did there, so this cannot be a neighborhood of that point, so because of this point it fails. Okay, let's increase dimensions. So let's take two intervals, A1 to B1 and A2 to B2, open intervals in R, and consider U to be the product of these two intervals as a subset of R2. Okay, what's this geometrically? It's easy to see. This is simply a rectangle. So here we would have A1, B1, let's say here A2 and B2. So we would get, so let's draw the boundary line here. So this, but we would only consider the interior of this rectangle, which means not the boundary line. So everything in here, and forget about the boundary line, so it's an open rectangle, very roughly. Okay, slightly messed up here, this is not that rectangular, but you get the idea. So this is, this set is U, so a rectangle without the inside of the rectangle without the boundary curve, so this one just removed. So, and I claim this is open in R2, and let's prove this. So, U is open in R2. So, how can we see that? So we take some point x0, y0 in U, and now we need to find sufficiently small epsilon, and for this we need to kind of to see for x0 and y0 for both at once, how far is it to the boundary of the rectangle. So if we have some point in here, for example, we take, okay, here we need to find some disk which is still contained in here, so we need to pay attention of the distance to the boundary here, there, and there, and pay attention that we take the small, the radius small enough to fit in there. So how do we see this? If this is the point here, x0, y0, so then just for bookkeeping, by definition, x0 is between A1 and B1, y0 is between A2 and B2, and now we do the same trick basically as before, but just so by here taking this minimum so that elegantly it fits, but this time in both directions. So put epsilon to be the minimum of, and now we have to pay attention. So for here we would need to have the analog x0 minus a1 and b1 minus x0. So in this case that will be the minimum of the distance from here to there and from here to there. Now the same thing vertically, we get y0 minus a2 and b2 minus y0. These are four positive numbers, so this is really the minimum of them is still positive. Now, then let's check that the ball is enough. So let's say we have some some xy, some point inside the epsilon ball, or in this case a disk here, around x0, y0. We compute the following. The distance, so x minus x0, the distance, the absolute value of the difference of the two x coordinates. This is small enough, namely this is, so now we use the same trick as before with respect to the Euclidean metric. This is the same as the square root of x1 minus x0 squared, which by monotonicity of the roots is the square root smaller than or equal to the square root of x minus x0 squared plus y minus y0 squared, but this is the Euclidean norm of xy minus x0 y0, and this, since we're in the ball, is smaller than epsilon. So, and analogously you could do the same with y coordinate. Analogously y minus y0 to the absolute value is smaller than epsilon. So just by definition of epsilon, this means x must be between a1 and b1, and y must be between a2 and b2, simply by just choosing this that small here that we cannot touch the boundary there. And so this means this is in U. So x, y is in U, and since the point was chosen arbitrarily somewhere inside the ball, this means B epsilon of x0, y0 is a subset of this open rectangle U. And this means, let me just squeeze the last few words here in there. We have seen that for every point we can find such an epsilon which might depend on the point, or which depends on the point. This is fine. But for all points there, this x0, y0, we have found this is a nice radius of the disk which fits in there. And this means that this open rectangle is open in R2. Okay. Now I have to erase, and then we discuss some properties of open balls and open sets in a more general way, but this will hopefully give you some examples for going on. Let me erase. The first thing I want to observe about open balls in an abstract way is that we define continuity with these epsilons and deltas, and it turns out if we just use this formalism of open balls, we can formulate this a bit more concise. Namely, so let me put this as a remark 1148. So assume x and y are metric spaces. I'm dropping the metric from the notation. Assume we have a map from x to y, and assume we have some point A in x. Then by definition, by definition of continuity, f is continuous in A if the following holds: for all epsilon bigger than 0, there exists delta bigger than 0. Okay, such that the distance of values of f is smaller than epsilon, meaning that the values of f are inside the epsilon ball around A. And now which values? So all points which are delta close to A. So sorry, not A, f of A. So, and here we just need all points which are delta close to A. So the image of f of B delta of A is a subset of the epsilon ball around f of A. I hope you understand this, because this is really precisely the giving the definition of continuity. Just for notation's sake, this is a bit confusing maybe, because this here is now an open ball in X, and this is here an open ball in Y. So this one refers to the one metric and this to the other metric, so I hope this is not confusing. So because this notation is used pretty often, unfortunately, to use B epsilon for the same balls for balls in different spaces. So I'm not changing notations here, but you can see this is a very, very concise way of kind of expressing continuity here, so that small balls are mapped to small balls, very roughly. Okay, now this is continuity, and now let's explore some properties of open sets. Okay, assume we have some metric space, XD, a metric space. First of all, open balls are open. This sounds weird, but B epsilon of x0, if we just take this as a set, this is an open set in X for all x0 in X and epsilon bigger than 0. This still needs to be checked, so we need to check that if we take some point inside the ball, we have a small little ball around this. I will draw you an image of this in a second. So then the empty set and the whole space, X, are open in X. Okay, not too exciting, I guess, these properties, and now it becomes more interesting. And it turns out these properties that I'm discussing here are actually useful. So it's not, it's maybe a bit weird, but they are really useful. So assume we have a family of open sets, UI indexed by I and I, family of open sets, sets in X where I is a set, so an arbitrary index set, which might be infinite and yeah, very, very, very big. But then the union of all these sets, so the union over I and I, ui, is again open. Okay, now this is for unions, and now we discuss the corresponding property for intersections, and it turns out it's not that good, but if we take finitely many, then the intersection will still be open. So if we take u1 to un open in X, then the intersection of them from I equals 1 to n ui is open in X. Okay, this is not true for infinitely many. I will give you the counterexample after the proof. Now let's take a look. So, okay, now you might think, what is there to show in part A? So open ball is so far just a name, but it's not clear that it's an open subset. Namely, if we consider, so let's assume we have some open ball, again, consider the two-dimensional example of radius epsilon. Now, we need to show that there's a neighborhood of every point. Namely, if we take an arbitrary point here, let's say here, X, we need to show that there is some open ball around this point, which is contained in the big open ball. This means basically we need to take some radius delta, such that the delta ball, which would be something like this, is still contained in there. So we just need to choose our radius sufficiently small. But this is not that hard, because we basically know what delta must look like. So take some arbitrary point X from the epsilon ball. Okay, and to get the delta, so the radius, if you take a look like this, so assume we would have the radius, this segment here that I'm drawing, I'll do it like this, this has radius epsilon. So the radius that our delta must have must be, this here must be plus this big segment here must be smaller than epsilon. But we know that this here, this segment has length, a distance from x0 to x. X is some fixed point. So we just need to take delta to be the difference of the big radius, so epsilon, minus the distance from x to x0. And since we're in the open ball, this distance is strictly smaller than epsilon. So this is really positive. Okay, then we need to show that b delta of x is really included in this big ball. Then for all points A in b delta of x, we compute that the distance from A to x0, and here we now can choose the triangle inequality, namely if we are somewhere here inside this small ball, the distance from here to x0 is smaller than this distance plus this distance. So this is triangle inequality then. This is so formally smaller than or equal to d of ax for this point x that we're studying, plus d of x x0, and so this is smaller than, so d of ax, a is in the delta ball here, so this is smaller than delta, plus d of x x0, and just by definition of delta, this is epsilon. So a is in the epsilon ball, in the open epsilon ball around x0, so this means b delta of x is completely contained in b epsilon around x0, and this means this ball here, the big ball, b epsilon of x0 is a neighborhood of x. So as x was arbitrary, this shows b epsilon of x0 is open in x. So the name open ball is a good name because it is really open in the sense that we study other open subsets. Otherwise, this would be very bad terminology. Okay, part B. The empty set and x are open in x. For the empty set, this is something I said before, the condition is empty. There's no point which we need to check. So since there is no point in the empty set, every point in the empty set, namely none, has a neighborhood which is which is completely contained. So the condition is empty. Is empty. Empty, not visible in the set. So I say the condition is void. Hence, always satisfied, so this is open. and the openness of X is trivial. Namely, if we take a point in X, we can always find a ball which is completely contained in X, namely every ball. So for every x0 in X and every epsilon bigger than 0, B epsilon of x0 is completely contained in X. And this means we have some open ball, so it is a neighborhood, so this already implies X is open. That's a triviality. C, arbitrary unions are open. So let's take a point in this big union. Let x0 be in the union I and I, ui. So in particular, we can find some index such that x0 is contained in the set corresponding to the in the set of the corresponding index. So then there exists some, let's call it I0 in I, with x0 in ui0. So, and this set is open. So u0, I0 is open by assumption. Hence, there exists some epsilon bigger than 0 with B epsilon of x0 contained in ui0. But since this is one of many, this is of course part of the big union. So this is a subset of the union over all I in I ui. So this union is a neighborhood of x0. So this means the union is open as the point was just chosen anywhere in this union, here, since x0 was chosen arbitrarily. Okay, part C, so this was not too hard. Part D, so take a point in this finite intersection, x0 in the intersection of the ui. This particularly means, if we rephrase the intersection differently, x0 is contained in ui for all I between 1 and n. And since the ui are open, then we know for every I between 1 and n, there exists some epsilon I, so such that the epsilon I ball is contained in the set ui, because each one of them is open. So epsilon I bigger than 0 with B epsilon I of x0 is contained in ui. So for everyone we have an individual. Now, this is for every ui separately, we have this epsilon I, so how can we find an epsilon such that it's contained in intersection, so in all of these I? And the idea is now, because all these epsilon balls have the same center and they might now bigger or smaller, we just take the smallest. We just put epsilon to be the minimum over all epsilon 1 to epsilon n, which is a positive number. Then B epsilon of x0 is a subset of each of the B epsilon I of x0, just by construction. And this is contained in ui for all I between 1 and n. And this, of course, means B epsilon of x0 is contained in the intersection of the ui. Okay. So, again, the point was chosen arbitrarily, so it follows that the intersection is open, which concludes the proof. Question to the non-existent audience, where did we need that we have finitely many, the intersection of finitely many? The point is here, when we take the minimum here. If we have finitely many positive numbers, the minimum will still be a positive number. If we would have infinitely many numbers here, we have to, of course, have to take the infimum, because the minimum might not exist. But the radius, the radii that are in there might become closer and closer to 0, so the infimum could indeed be equal to 0, in which case we wouldn't have such a ball. So there it would collapse. This minimum argument doesn't work for infinitely many. Okay, now, speaking of these infinitely many, let me give you a counterexample. So remark 1150. intersections of infinitely many open sets are not necessarily open. Not necessarily open. So there's a very simple example. We consider as a metric space simply the real numbers with the Euclidean distance, or the distance given by the absolute value, and put un to be the interval minus 1 over n to 1 over n. So this is of course an open interval, so this is open for all n in n. But if we take the intersection over all n in n u n, this means so the intersection n from 1 to infinity minus 1 over n to plus 1 over n. So what is this big intersection? What's in there? This would also be a question to the imaginary audience. What is the intersection of all these sets? I mean, this becomes smaller and smaller, and since these boundaries here tend to 0, the only thing which is contained in them for every n is 0. So this intersection would just be the point 0. And of course, there is no neighborhood of 0, so no epsilon balls, so no interval around 0, which is contained in this one point set. So this cannot be open. So which is not open in R. So indeed, infinite intersections might not be open. Okay, let me erase, and then we'll see that if we know the formalism of open sets, there is an extremely concise way, or a very elementary way of formulating continuity without making use of epsilons and deltas, but of course we have to pay the greater deal of abstraction since we have to study abstract open sets. We will see this after I erased. We can now characterize continuity in terms of open sets as follows. Consider theorem, what is the number? 1151. So assume in the most general setting we have two metric spaces, x with metric dx and y with metric dy, metric spaces, and assume we have a map from x to y, some arbitrary map. Then f is continuous, so continuous in every point. This is what I'm characterizing here. How I'm characterizing continuity in a different way, so assume it's continuous everywhere. This is the case if and only if the pre-image of an open subset of y, let's say u, is open in x, and this should hold for every u open in y. So a map is continuous if and only if pre-images of open maps are open, full stop. This is kind of the most general but very abstract way of characterizing continuity. In fact, this is even more general than the thing than the situation I discussed here, because so far we restrict to metric spaces, and there is a more general notion of spaces for which we can kind of very, very abstractly define something as points. Points nearby each other and so on. So we have this general notion in so-called topological spaces. For topological spaces, we don't have a metric anymore. We just have open sets. And by open sets, I mean basically a system of subsets, which we call open, which has the properties from one of the previous theorems where I showed that arbitrary unions of open sets are open and finite intersections of open sets are open. So in general, you can define topological spaces by having a system of subsets and axiomatically define this or demand that these properties are satisfied. Then you can really use this right-hand side here to define a continuous map, and so you can generalize some of the things we did before. So you can generalize convergence of sequences in such sets and so on, but this is the way we're not going to take here. And if this was a calculus course for mathematicians, we would discuss this there, but this is something you probably very likely don't need in your physics studies. I mean, metric spaces is already general enough. So how to see this? So how is this related to this? So far we haven't really brought together openness and continuity, but since both require something about epsilon balls, so it's maybe not too surprising that there's a connection between them. So let's establish that. Proof. So let's assume that F is continuous and consider first an open subset, and we need to show its preimage is open. So let U be an open subset of Y. Okay, and what we now do is we take an arbitrary point in the preimage here. And let x0 be in the preimage of U under F. So to show that it's open, we need to show that f to the minus 1 of u is a neighborhood of x0 for every such x0. So we need to kind of find a nice neighborhood and so on. So let's use what we have and then go from there. So we know that we have, so f is continuous, and we know that this that u itself is open. So since we know by definition f of x0 is in U, and U is open, there exists some epsilon bigger than 0, so we have some epsilon ball around this point here in U, so there exists an epsilon 0, bigger than 0, with E epsilon of F of x0, a subset of U. Now we can use continuity, because we have characterized continuity in this remark from above by knowing we have a delta ball which is mapped into this epsilon ball by F. So this is remark, what was its number, 1148. By that remark we had there exists a delta bigger than 0, and here we use the assumption that it's continuous, such that F of B delta of x0 is a subset of B epsilon around F of x0. I hope it's not too confusing, since B epsilon again denotes both open balls in X and open balls in epsilon in Y, but I hope this is fine. Now, if we have this inclusion here, we can just basically use properties of sets and preimages that we did in the first week of Mathematics 1. Just some set theoretic properties, namely, we then know that B delta around x0 is now contained, and if we now take preimages here on both sides, we know that a subset is always included in the preimage of the image of a set. There we don't need continuity or anything. This is true for every map, some standard relation. B delta of x0. And we always know that if this is included in this, then the preimage of this is included in the preimage of this. This is also some elementary set theory. So this is these statements about sets that I need here, they were all discussed in Mathematics 1, week 1, basically, or chapter 1 actually of the course. So this is now contained in the preimage of this. So this is contained in f to the minus 1 of B epsilon of f of x0. But we know by construction from the openness that this here was a subset of U, so this is again contained in f to the minus 1 of U. So we have found a delta ball around x0 which is contained in this preimage, which means so f to the minus 1 of U is a neighborhood of x0. And as x0 was chosen arbitrarily, this was just some point in this preimage there, chosen arbitrarily. This shows that f to the minus 1 of U is open. Okay, this is what we wanted to show. U was an arbitrary open set, so the preimage is open. Now, for the other inclusion. So this time we only know, and this might be more mysterious upon first sight, we only know that preimages of open sets are open, which is some really abstract set theoretic thing, and then want to show continuity. So, how do we get there? So of course we need to show continuity at each point. So again we let x0 be some point in X. Okay, and we let epsilon bigger than 0, and in the definition of continuity we need to show there exists a delta such that if the distance of x and x0 is smaller than delta, then the distance of the image points is smaller than epsilon. This is just really by definition of continuity what we want to show. Okay, so let's see, what do we know? So we first of all know that so here we need theorem 1149a. If we take the epsilon ball around f of x0, so now an epsilon ball in y, we have seen that this is open. Open balls are open, this is what we've seen, but this is open in y. So by assumption, pre-images of open sets are open. F to the minus 1 of this epsilon ball, be epsilon around f of x0, is open in X. So by definition of openness, we know it's a neighborhood of x0, so we know there exists a delta bigger than 0, such that B delta around x0 is contained in the pre-image of B epsilon of f of x0. And this relation surely implies that if we now apply f on both sides, so the image of something smaller is contained in the image of a bigger set, that's clear. F of B delta of x0 is contained in f of f to the minus 1 of B epsilon of f of x0. And this is simply, so composing it this way, this is always an equality to B epsilon f of x0. Okay, so this, this ball, the delta ball around x0 is mapped into the epsilon ball around f of x0. And by this remark that before, this means we have continuity. So this by remark 1148 again. F is continuous in x0, and x0 was just an arbitrary point in X, so we have shown F is continuous. Okay, so continuity is characterized by open sets. This might look a bit strange, but sometimes this is really a useful property, and if you might stumble upon this in some textbooks or explanations or lecture notes or wherever, so just keep this in mind as an important characterization of continuity. Okay, now we have defined open sets, but in the headline of this section we also had closed subsets, and this is what I'm going to define next, and this is in some way a complementary term to openness, and complementary is really meant literally because the definition is quite dull actually and might look a bit awkward or might look a bit, not very subtle. Namely, if XD is a metric space, a subset of X is called closed in X if the complement of the set X minus A is open in X. Oh great, how inventive. This now seems very, very dull because this is just very stupid characterization, but it turns out this is kind of, to handle this abstractly and to discuss closed subsets abstractly, this is a really good characterization because you can take basically properties of open sets and use them to convert them into properties of closed sets by showing stuff about the complements. But I won't go too much into detail on this. The good news is there is a more interesting characterization of closed subsets. This is usually the definition that is used, but you can characterize closed sets in a more, straightforward way. So, and this is something we have seen closed intervals, and So what are crucial properties of closed intervals that open intervals don't have? It turns out you can, this is basically, the most important property of closed intervals is now reflected in this theorem, which transfers this property to closed subsets of metric spaces, namely, if we have an arbitrary metric space and an arbitrary subset, then the closedness can be characterized as follows. So A is closed in X if and only if for all sequences in, let's call them Xn in A, which converge in X. So this is of course a sequence in X, which converge in X. We know the following. The limit of the sequence is again contained in A. The limit is element of A. And this doesn't hold true for open subsets, for example. I mean, the easiest example is the open interval 0, 1. If I take the sequence given by 1 over n, so from the second term on, we're inside this interval here. And so the whole sequence in the interval 0 to 1, it converges in R, obviously, so it goes to 0, but 0 is not included in this set. So by this characterization, the set, so the open interval is not closed. So this is the crucial property. If we would take the closed interval here, let's say like this, here we know that if a sequence lies, so all the terms of a sequence lie between 0 and 1, the limit also lies between 0 and 1 if it exists. So in this case, we would still be in there. So it's preserved under taking limits, and this is in many in many situations it's useful to have this property that if I take an arbitrary sequence and take a limit, I do not kick myself out of the set that I'm working with. So this is the idea here. This is how you can define closed subsets. But of course, we need to prove this, how this weird definition as a complement of an open set, how this works together with the sequence description. So let's prove this again in two implications. We first assume that A is closed and then want to show the sequence property. And we do this by contradiction. So assume, so A is closed, and assume there was a sequence in A, I have to name the sequence xn in A, which converges and such that the limit, which I call A, small a, so this is defined as the limit of xn, is not in A, so in the complement of A. Now, we know, since the set is closed, that the complement is open. So since A is closed, the complement is open, so this means there exists an epsilon bigger than 0, so that the epsilon ball around the limit is completely contained in this complement, such that B epsilon of A is contained completely in the complement of A, which of course is in other words given as B epsilon of A intersected with A is empty. Now, but this is bad. This gives a contradiction to the definition of convergence, because we know the sequence converges, but the sequence is in A, and if this holds, in particular, the elements xn cannot be in this epsilon ball. Whoops. So no element of the sequence is included in there, and that can't be right. Because, so this is a contradiction. Contradiction to convergence. Because by convergence, by definition of convergence, we haven't formulated this with respect to these balls, but we have seen that for each epsilon we have some n0, such that from this n0 on, all terms of the sequence have to lie within distance epsilon of the limit. So every such epsilon ball must contain almost every, so all but finitely many, terms of the sequence. So contradiction to convergence since B epsilon of A must contain all but finitely many of the dxn. So it follows that our assumption is wrong, so it follows that the limit A in A lies in A, and since the sequence was chosen arbitrarily, this proves the whole implication. Okay, for the second implication I need a little bit more space, so let me erase here.